Good morning and welcome back. In this next section in chapter 3, we are going to be looking at something called the mean value theorem, which looks a lot like the intermediate value theorem, um, but there are some pretty big differences. And we will also be looking at finding the derivatives of piecewise functions and then making them continuous and differentiable. For the most part, the derivatives, like finding derivatives, we already know how to do all of that. And that's throughout the rest of the year. We know how to find the derivatives of things. It's just going to be how we're using it. We're going to be filling in a lot of the applications and other things we can do with them. And so, the mean value theorem. First of all, what is the mean value theorem? The mean value theorem says that if a function is continuous on a closed interval, and it's differentiable on an open interval. Differentiable just means you can take the derivative of it. We'll talk more about that in a minute. Then there exists at least one point in the middle where the derivative at that point equals the slope of the tangent line between the two endpoints. Remember, the derivative is the slope of the tangent. So what this looks like graphically is if we have our 2 points, A and B, the slope of this line in between them will equal the slope of the tangent at some point in between those 2 points. Notice C is in between A and B. That's what the mean value theorem says. So how does that differ from the intermediate value theorem? The intermediate value theorem, we have a lot of the same language. We have f of x is continuous on a closed interval. We have something's between f of a and f of b. Here we're not looking at between, but we're subtracting. But we do have f of a and f of b. Then there exists a number c on the interval. There exists a value c on the interval, where c equals m, but here it's where f of c equals something. And so they have a lot of the same wording involved, but they have very different meanings. The intermediate value theorem is talking about the y value. It's talking about a point. The mean value theorem is talking about a slope. So when we're dealing with slopes, that's going to be mean value theorem. When we're dealing with does a point exist in between there, that's the intermediate value theorem. Getting the two confused is one of the bigger mistakes that people make with these types of problems. So knowing which one it is important. And also there are times when you can use the intermediate value theorem on the derivative of the function. So looking at the slope, it's like, hey, the slope is going from here to here, which means it's going to have to hit something in the middle, instead of using the mean value theorem. And that is a possibility for some problems, but not all problems. It depends on what we have or given, all sorts of stuff like that. So there is some overlap, but there's also some differences. So how do we use the mean value theorem? We can use it just like the intermediate value theorem to prove the existence of the point, at which point it's very, very similar. There exists a point C in the middle of A and B such that f prime of C equals the slope between the two endpoints. I mean, there is that, but most of the time today, we're not actually going to be finding the existence of the point. We're actually going to be figuring out what is that point. So we're going to be finding the C value that makes it true, which we're doing basically the same stuff, but it's less obnoxious and more entertaining. So how do we do that? We have a function. We want to find the value of C that satisfies the conclusion of the mean value theorem. So first thing we need to look at is it continuous and differentiable? It's a polynomial, it's continuous. It's also a polynomial, so it's differentiable. Again, we'll talk about differentiability in just a second, but yes, it is continuous and differentiable. So now we need to find the values of the endpoints. We need to find f of 1, which when we plug it in, f of 1, I found the first, f of 1 first, whatever. 3 plus 2 plus 5 is going to be 10. And we can find f of -1, slightly more difficult. We have 3x squared, that's 3. Then 2 times -1 will be -2 plus 5. So f of -1 will equal 6. Then we also need to find the derivative. F prime of x equals 6x plus 2. And so what the mean value theorem says is somewhere in between -1 and 1, 6x plus 2 will equal 6. We just need to figure out what that x is. We can subtract 2, so 6x equals 4. Divide by 6. X equals 4 over 6, or 2/3. That is in between -1 and 1. And it satisfies the conclusion of the mean value theorem. The slope between the endpoints, oh no, it doesn't equal 6. I forgot to find the slope. I knew I was missing something. Why didn't any of you stop me? We'll just erase this really quick. Ignore the last couple minutes and then come back. All right, the slope, 10 minus 6 over 1 minus -1. It's 10 minus 6 over 2, which will be 4 over 2, which equals 2. So what the mean value theorem actually says, for those of you paying attention, is 6x plus 2 equals 2. Now we can solve for x. Subtract 2, 6x equals 0, divide by 6, x equals 0. So one reason why I noticed the mistake there was because there's a theorem saying that the polynomial where it'll hit will be the midpoint of the interval, and so 2/3 or whatever was not the midpoint of -1 and 1. 0, however, is. So this would be the c value at which that satisfies the conclusion of the mean value theorem. Whew. All right, so that's the mean value theorem. Differentiability. What does it mean to be differentiable? Well, in order for something to be differentiable, it has to be continuous and it has to be smooth. Continuous means we can't have any breaks in the graph, even removable discontinuities, holes. We can't have any of those for it to be differentiable. It has to be continuous. And smooth means it can't have any corners or cusps. So if we were to look at a graph, let's graph it. Goes like that, and then starts here, and goes up like that, and then angles down here, and then goes like that. All right, there's a good graph. So we have a graph of a function. Where is it continuous? Or where is it differentiable? Well, just like where it's continuous, we aren't going to list all the places where it's differentiable. We're going to say it's differentiable everywhere except, so x can't equal -2 because it's not continuous there. 0 because there's a cusp, it's not smooth. And +2. So it's differentiable everywhere except for those points. So that's how we could tell from a graph where it's differentiable. How about for a piecewise function? We want to find the values that make it continuous and differentiable. Generally speaking, with non-piecewise functions, all of them that we work with are differentiable everywhere they're continuous. We don't have many sharp angles in our functions, with really the exception would be absolute value functions. They have the vertex. They're differentiable everywhere else, but they do have that vertex, which is a problem. So piecewise functions, find the values that make the function continuous and differentiable. So this is going to be very similar to what we did with continuity. In fact, it starts out the same because we have to make it continuous. We're going to plug that number in for the x values. So we're going to have ax squared plus 10. So that'll be a times 2 squared plus 10 has to equal 2 squared minus 6 times 2 plus b. We could simplify this a little bit. This will be 4a plus 10 equals 4 minus 12 plus b. So that would be 4 minus 12 is negative 8 plus b. And then I just move the 8 over so that we can combine it with a 10. So that would be 4a plus 18 equals b. All right, we have an equation with two variables. That's part of what we're doing. That's the continuous part. We also have to make it differentiable. For differentiable, we're going to do exactly the same thing, except we're going to do it with the derivatives. To take the derivative of a piecewise function, you just take the derivative of each piece of the function. If it's not differentiable at the intersections, you lose the or equal to part of the domain, but that's all it is. It's just the derivative of each part. So if we're looking at f prime of x, it's going to be 2ax plus 10s when x is less than 2, and 2x minus 6 for x is greater than 2. We're going to make it so that this is equal, so or differentiable, so we could have an or equal to there, but we don't stick with the derivative for very long. So we're just going to plug 2 into those now. So we'll have 2 times a times 2 equals 2 times 2 minus 6. So that would be 4a equals 4 minus 6 is negative 2. Divide by 4, a equals negative 1/2. We're then just going to plug that right back into that equation. So we have 4 times negative 1/2 plus 18 equals b. 4 times negative 1/2, that's negative 2, plus 18 is 16 equals b. So our answers, b equals 16, a equals negative 1/2, are the values that will make this function continuous and differentiable. So notice again how that was almost the same thing we were doing in chapter 1, looking at continuity. We just had the derivative part as well. The derivative is usually easier to plug stuff into. You have fewer terms, like notice the whole b term went away when we took the derivative. It is possible that it wouldn't, and you'd end up with a system of equations that you can solve, but we know how to solve systems of equations. So